Exactly. Yeah. So let's remember where we were. We looked at these L chi S things, which by definition is a sum over prime sum over k 1 over k p to the ks. No problem with this definition. The key fact, of course, is that the exponential of this thing is the L function, the actual L function. And then we looked at sum over all chi mod q of chi of a bar, 1 over the number of these characters, phi of q, of L chi s. And we saw that this was at least a leading order, a sum over the primes congruent to a mod q, 1 over p to the s, plus things that remain bounded as s goes to 1.
Alrighty, we're going to prove the continuous version of the chi's. Yeah,
that's exactly what we're doing today.
Yeah,
yep. Okay. So so in order to get this to diverge, so we showed. So I owe you, as you said, two things. If assume that the L chi s's are entire, this in particular means that the real parts of the L chi s's do not go to infinity, since then their exponents can't go to infinity. So this is not an assumption, but I have to prove. Need to prove, maybe is better than assume.
Right.
Need that these things are entire, they have no poles. That implies that this doesn't go to infinity. And if chi is complex, so if it's not equal to its conjugate, then we show that the real part of L chi s doesn't go to minus infinity either. And this expression is real. And so the one character, of course, one chi is chi 0. We know that L chi 0 s does go to infinity. And with the initial constant chi 0 of a bar equal 1 for any a coprime to q.
Right. And then this like eliminates the complex ones.
Exactly.
And it leaves the real bits, right?
Yep. And then the next thing we'll need is that L chi real. That's L chi real. If chi equals chi bar, then this at 1 is not equal to 0. So we know that it doesn't go to infinity, and hence the real part of L chi s doesn't go to minus infinity. So if this doesn't blow up, we know that none of them blow up to plus infinity. The complex ones we already know don't blow up to minus infinity. We need to know that the real one also doesn't blow up to minus infinity, in which case we conclude Dirichlet's theorem.
You're going to do that through like class number form.
And we're going to do this through class number.
What was the equality you promised us with this? It was like L chi 1 is equal to.
So there's two cases. Let's build up to it.
Okay.
Let's build up to it. We'll see the calculation of how you might guess such a thing. Okay. So so let's work on this. So we have to show that it's entire. So the obvious thing, well, it's not the obvious thing because it's not the thing that Dirichlet did. But now for us, the obvious thing, we use Riemann's method. So it's we're achronological. Use Riemann's technique.
Or anti-chronological. Or
Yeah. So we'll make a theta function. Theta of f chi of t will be a sum over n positive of chi of n f of nt, which is just a twisted Poisson summation. And so Poisson summation tells us that twice this theta function. Notice that chi, if chi is anything other than all ones, chi of 0 is always 0. 0 is not coprime to any number. The GCD of 0 and any number is that number.
Except the trivial modulus.
Except the trivial modulus. Right. So chi of 0 equals 0. So we don't have to take out 0. And I'll make one more thing. So if I need to put it somewhere.
I also feel like the calculation's even cleaner for like these Dirichlet characters than for zeta.
Yes, in some ways, yes. If chi is even, that is chi of -1 is 1, in which case chi of -n is chi of n for any n, then take f to be even, so that their product is even, else take f to be odd. Okay, so f even you can think of, for example, let's see. The nice thing about this is
You don't want the theta function to vanish.
I don't want the theta function to vanish, and I want it to be a sum over all integers. So f even, we can take the example, f even could be e to the minus pi t squared, f of t, the Gaussian. And f odd, how do you make the Gaussian odd?
You get t.
Yeah, just throw in it's even, throw in a t in front.
You see, the interesting thing here is that, right, what Bump does is that he adds a t to the formula of the theta function instead of to the test function. Instead of what he does. I guess it's all the same thing, right?
It's all the same thing. Exactly. It's all the same thing. This will be an odd function. Odd times odd will be even. Even times even is even. So I want to make this even. Okay. So Poisson summation, if I double this, now I'm summing over all the positive and negative integers, and 0 is there too, except chi of 0 is 0. Then this is a sum over n and z, chi of n, f of nt. And we need to get something on the other side, but in order to get something on the other side, we need to extend. So need to extend chi to from a function from the naturals to the complexes to a function from the reals to the complexes. And there's a very natural way to do this, okay, which many of you know already. But let's do it anyway. So the idea is, as always, spectrally. Do things spectrally. So finite, so Fourier transform, Fourier analysis, but now finite. We're about to get to Gauss sums, yeah. But first, let's just do Fourier analysis in general terms. If I have a function from z mod q to c, what is its Fourier transform? So the Fourier transform, the definition I would first come up with is, well, you just take the function, you multiply it by e to the 2 pi I over q rm and sum over r mod q. I'm going to add a normalizing factor, 1 over root q. So this will be my normalization for the Fourier transform. There's a very good reason for this. The reason I like to do it this way, the rationale, well, there's a number of different rationales, but my preferred one is to have a clean Parseval. So Parsival identity, so this is a claim, Parsival identity, which will now read that the L2 norm of f is the same as the L2 norm of its Fourier transform. In other words, taking this Fourier transform is an isometry. The other one's not. It changed this Fourier transform. This normalization makes the Fourier transform an isometry. Is
nice.
Isometry. So it measures the distances, the length of f as a vector in Hilbert space, and L2. So f is in L2 of z mod q. This is our nice finite dimensional Hilbert space now. It's a very funny way of saying, give me any complex number attached to a point. But anyway, these things are all the same. So let's prove this. Why is this true? So let's prove it in the squares. What is the L2 norm? It's just the sum over r mod q f of r squared. That's easy. What do we get on the other side? And I want to know that these things are equal. On the other side, I get a sum over m mod q. Well, f hat of m norm squared. So that's 1 over root q, sum over r mod q, f of r e q r m, all squared. Okay, so this is f hat of m squared. And the L2 norm, well, the square of the L2 norm is just the sum of the squares of the things. Does that make sense? I guess I could define, some people would like to define the L2 norm here with a different normalization instead of keeping the normalization in the Fourier transform. But I can't remember that. I'm not smart enough, so I have to just do it this way. So we have a absolute value squared with a sum inside. What do we do with that?
Do it in bar on bar.
Exactly. We want to open the square.
Yeah.
Just realized my computer's going to run out of juice, and I didn't plug in. Here we
It's the
go.
incredible thing about complex numbers, right?
Exactly. Exactly. So we're going to open the square and reverse order. So when I open the square, I'll have a sum over two variables, an R1 and an R2. I'll have an f of R1, f of R2 bar. There's a 1 over q. Actually, let's put the 1 over q right here. And then a sum over m with an e to the 2 pi I q rm and R1 m, and R2 is the one with the bar. So this is an e to the 2 pi I R2 m bar. Okay.
You have the divisibility condition.
And this sum is a complete sum. And this is really, of course, this is EQ of minus of m times R1 minus R2. And this picks up, this is exactly the indicator function of whether R1 is equivalent to R2 mod Q. And if it is, so we get 0 unless they are equal. And on the diagonal where they are equal, I get exactly the sum of the squares of okay. So that's the proof of Parseval.
So nice. Wait, so in the very general Parseval, right, with, I mean, not very general, but saying like the L2 R case.
Oh, look at this. I have all this room. Huh. Okay. Yeah, I'm listening.
So in the L2R case, does this like, does technically work just the same way?
Just the same way. Well, you mean the proof?
Yeah.
The proof, when you reverse order, is now you have an integral.
Right,
if you do it naively. So you, again, if you want to do it the right way, can take a couple of derivatives so that you get things that converge and then undo those derivatives. So you have to work in these Sobolev type spaces.
But here we have
Here it's a finite sum. Everything's very easy. Okay, so that's the finite Fourier transform. What's the Fourier inversion? Since I have room here, is there a Fourier inversion?
Is your version of the inversion? Is it an involution or is it like of order 4 or like?
In other words, the Fourier transform. So I want to do the same Fourier transform but with a conjugate here. In other words, the inversion formula will read if I take the claim.
So people have the transform gives you the negative.
Exactly.
Like do it another couple times.
Exactly. So I won't do a transform again. I'll just do an inverse transform. So it's a sum over m mod q f hat of m e of minus mr with the normalization factor 1 over q. I claim will recover f of r.
That's pretty smart.
And it's just again, you open up what this is. Let me leave this as an exercise. Let's not spend time on this. But again, you open up the sum, you use this, there's a 1 over root q here, there's a 1 over root q there, that gives you the identity, and I gave the proof.
It's probably, this kind of thing wouldn't work for quaternions or something like this, right? Or I'm just thinking like this trick, right, of you taking like conjugate, right? It just comes up so much in this sort of Fourier stuff.
It's all over the place, yeah.
I wonder like if any analog could be.
But it's a general, this is something about Hilbert spaces. We're seeing baby versions of it, but this is a general fact about anything that's a Hilbert space. Nick.
Does the 1 over root q come from like some kind of normalization on C by QZ? Like trying to make the measures work out?
Well, so there's a better reason for the 1 over q, which is there should be square root cancellation along these things. And this, so in other words, the sum of length q, if these things are coin flips, should have size root q. And when I divide by root q, that normalizes the transform to be of size 1. But really it's here, it's the number of elements.
Right.
So I would get just Q if R and if R1 and R2 are equal, the sum would be Q.
Then you'd be
So it's
stuck,
like-
right?
It's like sort of the sum of the weight of the elements squared something.
Exactly.
Ends up being one. Okay. Because if you use like the right exponential in the real case, you don't get that 1/q, like the usual Fourier.
That's right. But if you, so that's why I said when I do Fourier transforms, I always put an e to the minus 2 pi I x y or whatever as the thing that you integrate against. And if you don't put the 2 pi I, if you just do e to the minus I x y, then there's like 1/√2 pi's that are flipped. Exactly.
No, you want the 2 pi, but like we're using the 2 pi.
We're using the 2 pi, but
We also have a 1/√q.
yeah,
Okay.
if you like, maybe the right function is not this function, but this over root q.
And there's also like, isn't there like some sort of Gauss sum related thing where
We're going to use
related
this.
to this as well?
We're going to use this exactly for Gauss sums. That's
Right,
exactly
so like
right.
the 1/√q also is relevant for that,
Absolutely,
right? So it's like, yeah,
absolutely.
it just like kind of comes up everywhere.
Yep.
Okay.
In fact, let's do that right now. So the key idea is we have this character, Dirichlet character. Okay, so other questions on these finite Fourier transforms? So far, so good? Let's see. I think now I should be able to
Oh,
pin.
Lewis is there.
Pin.
Yeah, pen, right?
Where is it? It's
On
not pin,
top
it's
of- Oh, it's not pen?
it's
Oh, spotlight?
spotlight. Let's see. I wish I was better at this. Okay,
Are
let's
you
try
the
pin.
host of your?
I
meeting?
must be the host. Yes, I'm the host. Why can't I spotlight? I don't know. Okay, whatever. Let's
Yeah,
move
let's
on.
say you're the host. It's really weird.
Okay, so so what are we going to do? Let's take the Fourier transform of the Dirichlet character.
Right.
So idea, what happens if we try to expand chi as Fourier in its Fourier series?
Which is really all mimicking what we were doing with Poisson summation originally. Really, we're trying.
Yes, but now we're sort of going to mix the finite Poisson summation with the Z's Poisson summation.
Right. But you can't do that if you don't have these analytic properties of chi. Right?
Exactly.
That's sort of like the issue. You can't just, do something. right?
Well, it doesn't make sense
Right,
until we.
right.
So what is the Fourier transform of chi? Well, as we said, 1/√q, a sum over r mod q, chi of r, e to the 2 pi I over q, r m. Okay. So if m and q are co-prime, this is a big if, then I can make a change of variables. So first of all, the only thing that occurs here, this is also equal to, let me separate these out. They'll differ by one little mark. That.
Right, like that, you meant the coprimality.
The coprimality. So I want to remember that it is a finite Fourier transform in Z mod Q, but because chi vanishes for numbers that aren't coprime to Q, only the R's that are coprime to Q will contribute here anyway. And then I can make a change of variables. R goes to, well, either way I can make a change of variables, but R goes to R m bar.
This is within the multiplicative group, right? And so you just cycle through it.
It just cycles through the multiplicative group. So this is equal to 1/√q, a sum over still r mod q, since this range is over the full group. Chi of r m bar, which of course is going to split in a second, e to the 2 pi I q r,
Right.
because there's m bar times n. And look at what this is. This chi of m bar pops out, and what's left is exactly the Fourier transform of 1. So the weird thing about these multiplicative characters is they have one Fourier transform. It's only the Fourier transform of one that matters. It's not the full, it's just chi times the Fourier transform of one. The Fourier transform of one has a special name. It's the Gauss sum. Exactly. So this is exactly, or without the 1 over root q. So traditionally, the sum over r of q, chi of r, EQR, which I would say is root q times the Fourier transform of one. This is called the Gauss sum.
Then it's to make sure it doesn't vanish, right?
We're going to do that as well. I have a slightly different point of view on that as well. Okay, so and this has a notation, standard notation. Tau of chi is the notation for the Gauss sum. As a little aside, what does this have to do? We sort of we know the Gaussian distribution, right? E to the minus pi x squared is the Gaussian distribution. What does this thing have to do? This.
Oh, what I was going to ask earlier was the coin flips thing that you said about square root cancellation. Is that heuristic just purely a probability kind of a heuristic?
I was only meaning it in the pure probability sense, but we're as
ends up happening like
it will be the actual truth in all the cases that we study. Right. So what's this summing over x squared? What does that have to do with this sum? So this is just an aside observation, maybe a historical one. If chi of r is the Legendre symbol, which I remind you is 0 if r and q have a factor in common, 1 if r is a square mod q, and -1 if not. Then what is this Gauss sum? Then tau of chi, it's a sum over all r, chi of r, e sub q of r. I claim I can add a 1 in here. Why is that? So how come I can stick in a +1? Well, if you multiply this out, what's the sum over all r of 1 times e of q? You're summing all the qth roots of unity.
Right.
So 0. So I'm just adding 0.
Yeah.
Okay, so I can replace chi by chi plus 1. What is chi plus 1? It's chi plus 1 is 1 if they're let's say q is prime. Let's say q is prime. It's 1 if r is 0. It's 2 if r is a square, and it's 0 if chi is not a square. Let's make that mention. 1 plus chi is equal to 1 if r is 0. This is when q is prime. 2 if r is a square, and 0 if r is not a square. In other words, it's the number of solutions. This is number of solutions to x squared minus r equals 0 mod q. Right? If r is equal to 0, then how many things square to 0? Well, just 0 squares to 0.
Oh, right, it's a square, then you have 2 solutions.
If it's a square, then plus and minus give you that same solution. And if it's not a square, there are no solutions.
Okay.
Okay, so let's write this sum as a sum over all possible squares. In other words, all a mod q of e sub q of a squared. If a is equal to 0, we get 1 contribution. Anytime r was a square, you'll get 2 values. You'll get a and negative a. Will both contribute those 2 values. And if it wasn't a square, well, then it never occurs.
Okay.
Isn't that fun?
Yeah, this is a big piece, but in general, right, you have to assume that you're outside of a Legendre symbol.
Right. This is just
For
for the
case.
real character. I just want to connect to why it's what the Gaussian distribution has to do with this. It's a sum of x squared, e to the x squared, and this is a sum of e to the x
So
squared.
this is sort of the connection.
That is a connection, yes.
And I was about to say, like, okay, but what are, yeah. Yeah, but this is just the observation.
Yeah.
Oh, okay.
Just an aside.
That's pretty cool. Okay.
Just for your general knowledge. Okay, so we have this thing. What about if M and Q are not one? What if M and Q have a factor in common? So this is where things get interesting. If M and Q have a factor in common, well,
So what have we proved so far? If they are co-primed, then,
if M and Q are co-prime, then
right, then you
the
got this formula.
Fourier transform is just the Gauss sum times chi of n.
Exactly.
Okay, that's the formula. If they're not co-prime, let's look back at what this Fourier transform is. Sum over R, mod Q, chi of R, EQ of Rm. Well, funny things can happen. So here, this is the only place where we'll make the distinction between primitive and imprimitive characters. Everything else that I have to say is a general fact about functions on Z mod Q, on the Hilbert space. Here, you can get some weird behavior unless, so if Q and M is bigger than 1 and chi is primitive.
Yeah, then it works out well.
And chi is primitive.
In fact,
Primitive.
it doesn't even work out like the imprimitive piece.
That's right. And neither will I, because it really depends on whether you see there's so many things floating around. There's Q, there's the Q divided by the GCD of M and Q,
Right.
and then there's the conductor of chi, which is where it was induced from. And all of those things can be, it's a complicated mess to write a general formula. And it's not even so, it's not so useful.
Right.
So this is the one place where I will assume that chi is primitive, and I'll try to distinguish between what holds in general and what doesn't.
What is primitive mean again?
Sorry, so primitive, let's remember what that means. If you have a divisor Q1 of Q, and you have a character chi1 mod Q1, you can always induce a character chi mod Q by saying chi of n is equal to chi1 of n or 0 if n, well, this is if n and q have a factor in common, and this is otherwise.
It's sort of in a sense of it's a character modulo another number.
Exactly. We should do an example just to see what this is, and then we'll come back and finish this calculation. What's the first modulus that has primitive characters? Maybe 12?
6, I don't know, 12, yeah.
Yeah, 6 is too small, but 12 is just right.
12, right.
Let's try Q equals 12. So what are the characters? What's the group Z mod 12? Z mod 12 cross. You have
It's like 4 elements, right?
not 2, not 3, not 4, 5, 7, 11. Okay. And what's the group structure? 5 squared is 1. 7 squared is 49, which is 1 more than 48 is 1. So the structure is Z2 cross Z2. It's the Klein 4 group. Okay, the multiplicative
Why
structure.
is that called the Klein 4 group? I never understood why.
As opposed to Z mod 4, the cyclic group Z mod 4, Klein liked this group, studied it. It has all kinds of things have weird names. I mean, obviously people long before Klein studied this group.
Right.
Anyway, so what are the characters? So I need 4 characters, chi0, chi1, chi2, chi3. All of the elements are squares. So the only question is, let's see, I have 1, 3, 5, not 3, 1, 5, 5, 7, 11. Okay, so the trivial character just gives 1s to everybody. Every character gives 1 to 1. So chi1, we have options for what we do with 5 and 7, from which 11 is determined, because 5 times 7 is 11. Let's see if that's right. 5 times 7, 35 is -1.
Exactly.
1 less than 36. Okay, so they could both be 1s. They could be a 1 and a -1. They could be a -1 and a 1, or a -1 and a -1. Those are our 4 options. And then the value of chi has to multiply. So -1 times -1 is -1. -1 times 1 is -1. And -1 times -1 is 1.
I have to check consistency, right, for other moduli.
For modular other than 12, you mean?
Right, yeah, the dividing ones, yeah.
Yeah, you'd have to, yeah, exactly. You'd have to work out, in general, what's going on. But here, my question is, one of these is imprimitive, and which one?
Okay, I see it.
I mean, this is also imprimitive because it's a trivial character, which implies it's really its conductor is 1. This is imprimitive, of course. Who else is imprimitive? Yep, this is a character mod 6. Imprimitive. It's really a chi mod 6. Right? It's 1 on 1 and 7, which is 1 mod 6. It's -1 on 5 and 11. All the other ones, the only divisors, you don't have so many divisors of 12 to worry about. So once you differ at 1 and 7,
It's good enough.
that's it. So these are the primitive ones.
There's a nice calculation of how many primitive characters you have, right?
Exactly. Yeah. Maybe this is a good exercise. So here's a really good exercise. Maybe I'll put it here. So in the interest of time, let's make this an exercise too. So if chi is primitive and m is co-prime to q, it's easy to show that chi hat of m is in fact 0. But in general, it will not be. So I'll leave this as an exercise. And let me give you another exercise. Compute chi hat of m for all the possible values of m for chi 2 mod 16. What am I saying? Mod 12. So here's our imprimitive character. Compute its Fourier transform for various values of m. You have as m ranges in Z mod 12.
Like vaguely related to some class number kind of things. Or maybe I'm just making stuff up. There were like these sums, right? And you'd be able to evaluate it explicitly, like.
It should be related to class numbers of non-fundamental discriminants. So if the discriminant has extra factors, I wonder if that's right. I'm not sure. I think what I'm saying is right. Because if you have an imprimitive character, even the class number formula still applies appropriately interpreted. And if I'm right, then the appropriate interpretation is that it's the class number of a non-fundamental discriminant. I have to think about that. Louis, do you know off the top of your head? Anyway. Okay. So
Sorry,
this
it took me a sec to get to my
yeah, go ahead.
button. I don't know off the top of my head. The only other thing I was thinking about is like once you start looking at orders and stuff like that.
Once you start with what?
Looking at orders in the
Uh-huh.
fields instead of like instead of the whole ring of integers.
Sure.
Maybe it comes up there too.
Right. Okay. All right. So what have we? So now let's look at the Fourier inversion formula. So what does Fourier inversion say? So look at Fourier inversion. Fourier inversion says that if I take a sum over m mod q, 1 over root q, chi hat of m E of minus M R, and I add all this up, just like this is true for any function, I'll recover chi of R. It's true for any function on Z mod Q, but we actually know more about what this is. This is 1 over root Q, a sum over M. I know what this is. This we just showed. So first of all, it's 0. So if chi is primitive, then this is 0 unless M is coprime. So I can put a prime here.
And you can factor.
And if M is coprime, we showed that this factors as chi of M bar times, let's see, is it root Q? Is it root Q times the Gauss sum or 1 over root Q times the Gauss sum? So this is chi hat. The Gauss sum, where's my Gauss sum? The standard Gauss sum does not have, so chi hat of 1 is the Gauss sum divided by root Q. Good, that's exactly right. So I have the Gauss sum over root Q. And those root Q's can group together. Exactly. And now the Gauss sum comes out. So I get a tau of chi over Q and a sum over M mod Q, chi of M bar E minus M bar. That's just Fourier inversion, the Fourier inversion formula mod Q. Am I missing something?
No. I think you're good. The thing is that like vaguely recall something about dividing by the Gauss sum.
That's Bump's treatment, divides by the Gauss sum.
And then he has to like go into this entire thing about does the Gauss sum
Vanish.
or not.
Yep.
And you
There's
just
no
avoided that?
there's no need for that.
Oh.
It just directly follows from Fourier inversion.
Why did he do that?
I think it's closer to the historical treatment.
Sometimes I wonder if it's it generalizes to some other argument or well, what is it? I mean, but this seems more general.
Yeah. I like this treatment.
Okay, so then you have to do anything because for him he had to divide, then he had to bar on both sides and like.
Yep. It's just standard Fourier analysis.
This is it. This is the
Fine.
continuous version.
And now the whole point exactly is that this is a function. This is a function we've realized a multiplicative character as a linear combination of additive characters. As in the E's. And here, there's nothing wrong with setting R to be a real number or a complex number. It's a finite sum. So this is, if you like, the analytic continuation, although there's nothing analytic about it. It's the continuation of chi from the naturals to the reals.
Right, and you told us once it's not unique at all, right? There is like other ways to interpolate between the.
In principle, there could be, right? I'm giving you a function on the integers, and I'm saying, give me a function on the reals.
Right.
Take any function you want that goes, yeah. But this is sort of the right way, the natural way to do it because it gives the properties that we want.
Right.
And it gives the analytic continuation, as we'll see in a second. Okay, so
So
far,
actually, so this is something that Bump emphasizes in the book, right?
Bump emphasizes?
This like extending chi to be a function on the reals or something.
Yes.
So I always thought that was kind of a funny remark because I've never really seen that come up anywhere else, you know?
Huh.
And I sort of felt like, I guess I thought the more natural thing to do would be to like, you know, I think he's like proving a twisted Poisson summation formula. So like,
Yes, exactly.
I thought like, if you just do it with like exponentials, right? Those are kind of already functions on the reals. And then you can twist by the exponentials and then chi is just a sum of exponentials.
But isn't that exactly what we're doing here?
Yeah. I mean, it's I'm not saying anything really deep, I guess, but like, I just think it's kind of a funny thing because
I see you're saying, forget about the fact that you extended chi from a function on the naturals to the reals, just use this formula and stick it in
with the exponentials. Yeah, right. And then like prove, if you want to call it like Poisson summation twisted by
by
additive,
character,
by additive characters.
by
and
additive
then-
characters, right?
Yeah, and then some. So I guess like his comment made me think that like this would come in handy in other places, or there was like other instances of this happening, but I don't think I've ever seen anything like that.
Yeah, I mean, this is can be a completely general treatment. I'm doing it in the simplest case, but
Yeah.
we're just doing finite Fourier analysis, so, okay, if you have some group character inversion formula like this, this is a process by which potentially multiplicative character can be realized as a linear combination of additive characters, and then if that group is really the quotient group or something, then now you have access to a function on the entire group as opposed to the discrete subgroup. Does that make sense?
Okay.
What I'm saying?
I think so. Yeah. Okay. So
Yeah.
maybe in that context, then it would be, like you said, kind of completely general.
Yeah, you have a function on you have like a representation. Well, you have a function on the
On gamma.
I guess on gamma, and you can express it as additive characters on G mod gamma, and then that allows you to extend it back up to a function on G, something like that.
Okay. Yeah, I see what you're saying. Yeah.
Yeah, this is
Okay. Thanks.
a little bit like what's it called? Functional analysis theorem.
Peter Weil?
No, I was just thinking really, really basic. The Hanbana, bit of like extending up kind of thing.
Yeah,
Okay, I have a question.
sure.
Okay, so we started with chi, we defined it on n, but when we took our Fourier transform, that sum, our co-prime to q,
Yes.
are we summing that over n or over z mod qz? Over z mod qz, right?
This is over Z. So this is the funny thing. The sum is absolutely over Z mod QZ.
Okay, so that's just a finite sum.
That's a finite sum.
So chi hat was already defined over reals or complexes or whatever we wanted.
If you like, yes.
Okay, you could.
Yeah,
insert
chi hat
n.
can certainly be defined over.
Okay. Okay, and then so that's fine that chi is definitely square integral, square summable over chronic group. That's
Yeah.
fine. When we, okay, so when we take inverse, now we want to put in real or complex valued entries. Is this thing L2? Well, the extended chi, is it square integral?
Well, square integral on what? You see,
Well, now we define it over R.
yes. So, well, it's an exponential function, right? It's a linear combination of exponentials. So these things are never square integral over R. Its absolute value is norm square is, I mean, it's not just it's a bunch of things of absolute value 1 that you're adding up
Okay. and
over
we're
different
okay with
values of
that?
R. What's that?
We're okay with that?
Well, so remember, when we go to use this in Poisson summation, twice this,
Twisted against a nice function. Right? That's-
exactly. This is going to be a sum over all integers, chi of n, which we're about to replace by this formula, times f of nt. This has tons of decay.
And F has decay.
F has decay, so there's no problem with the sum because of f, not because of chi.
As long as chi isn't like super degenerate or anything, it's like never run into an issue.
Right. And I wanted to, since you made the remark, let's just observe the reason a lot of this is happening is, again, this interplay between the additive and multiplicative groups. That we have this ring structure. We have an additive structure where we have additive characters, but we also have a multiplicative structure, and we're sort of twisting one by the other. Okay. Great.
Okay, I think I'm okay with that.
Great. Okay, so let's put in what chi is, which is right here. So if I stick that in for chi, the only thing that has an n, which is now an r, the only thing that has an r or n in it is this last term. So it's a sum over, let's get out this stuff, tau of chi over q, a sum over m mod q, which is just a finite sum, chi of m bar, and then we have this. And so now I'll have a sum over n and z, e to the minus 2 pi I m n f of nt. So I just put in the definition of chi.
And you swap the sums.
And I swap the sums. I already just knee-jerk instinctively swap the sums. Okay. So now we're going to apply Poisson summation to this thing, which we can make complete sense of. So Louis, this is what you mean by just put in the additive characters, and then it's clear that you can take Poisson summation, right? So just to continue the calculation. So this sum of whatever function this is also equal to, so now we're applying Poisson summation, is also equal to a sum over, let's see, I'm using m already here. Fine, I try not to use, okay, let's make it k. I try not to use the same variable on the geometric side as the spectral side. So this is k and z. Let's make that an answer k. Of the Fourier transform of this. What is the Fourier transform of this? Well, it's you take this function, you replace n's by x's, you multiply by e to the minus 2 pi I x, or a plus, I forget. I think I do plus for the transform and minus for the inverse transform. We're integrating over x and r, and the Fourier transform is against k dx. So this just literally is the Fourier transform of this thing. And we sum over k.
Okay, yeah, so you went straight to the.
I went straight to the
side.
definition. I went straight to the spectral side and straight to the definition of the spectrum of the Fourier transform.
Simplified all there.
Exactly. Okay. So what is this? All right, we're going to make a bunch of change of variables. So first we can change variables. X goes to, let's make a change of variables. X goes to x over t. In this sum.
Wait, where's the t?
We're dilating f only by t.
Oh, it's the argument of the theta function.
Exactly. It's the argument of the theta function.
Right.
So we snuck that t into the theta function. Now we're summing over integers but twisted. We put out what chi is, and we replaced x by x over t. So that's still an integral over r. I have now an f of x. E, these I can combine. These two things I can combine. They both have x's in them, so that becomes x over t times what? I have a k, and I have a minus m over q. And this is, oh, and dx is dx over t. So there's a factor of 1 over t. That comes out. Did I get that all right? T is a positive real number. I think that's right. The x's here and here turn into x over t. There's a k that went there. There's a minus m over q that went there. And f became f of x, and dx became dx over dt, or dx over t. But this, we know exactly what this is. It's just f hat at, let's combine this. If I put the q on top and bottom, then I can say q k minus m over t cubed.
X being the, right, this.
X is the variable that we integrate out.
Against, and the rest of it being the variable.
Yep. So that is what the Fourier transform is. It's you integrate f against this variable. Okay. So all together now, what do we have? Chi of tau of chi, Gauss sum over q, a sum over m mod q.
We're gonna take the t out.
Sure, let's take the 1 over t out. Chi of m bar, and then a sum over all k, f hat of q k minus m over t q. Then there's one final observation, which is that we can group these two together as well.
So it's Q to be, oh, where are we taking Q to be?
Q is the character of chi. Q is fixed. Chi is a primitive character because we use the inversion formula.
Oh, okay, okay.
And M is mod Q.
Right, so this, you're gonna be able to like group this as a
Exactly.
Yeah.
Exactly. So the point is, as K runs in Z and M runs mod Q, this thing, QK minus M, also runs through all of Z.
Right. And then
These are the residues mod Q, and these are the shifts by Q. So if we put that together into one variable,
T is fixed, all right. So it doesn't
T is fixed.
mess around with that.
T is fixed and T is in the denominator anyway.
Right,
So if we make that variable, what should we make it? L?
yeah. Not repeat,
L in Z.
it's not-
Then this is F hat of L over TQ. And observe that this M bar is also equal to M plus, let's put it here. This is also equal to chi of M minus QK bar,
yeah, 'cause they're minus.
or M bar minus QK. I don't know how you want to write this, but the point is that this is just going to be A bar or negative A bar or something. L. So this is chi of, am I getting this right? If that's L, then this is negative L bar. I think that's right. And then we can pull out a chi of -1.
Right, yeah, there's some kind of -1.
So in total, something you don't like me?
So why do we get minus L bars?
Oh, because this is L,
Oh, okay. so you get
Stuff
minus
up
L.
there is minus.
Sure.
then this is minus L.
So you're sort of shoving in the interior of the sum to that, group it all together.
Exactly. So now the whole thing, becomes, what was it, twice theta of F twisted by chi of T is equal to chi of -1 tau of chi over TQ, and then a sum over L. Let's see, chi bar of L, and then F. Can I sneak it in? F of L over TQ.
Okay, and then, the factor of 2 on the theta function is just from evenness, right? Is that,
Yeah, the theta function I defined to be a sum over the positive integers. Where is my theta function? Sum over the positive
oh, the
integers.
positive sum.
And so chi of 0 is 0. And I chose F to have the same sign as chi. So I can extend this sum from the positive integers to all integers.
Oh, right, and that's why we're having that factor. Okay.
And that's where the factor of 2 is. Okay, but now we can recognize the left-hand sum also. I mean, the right-hand side. This is also by the same, so chi bar of L is also 0. Chi bar of 0 is also 0. And F and chi bar have the same parity. So this sum is even. So this is equal to twice chi of -1 tau of chi over TQ.
Get rid of the 2 on this.
Exactly. You can get, well,
F hat over L over TQ.
F hat of
Yeah.
of TQ. Very, very important. Thanks. So the point is, this is theta of F hat chi bar, and not at T, but at 1 over TQ.
The,
So that's the functional equation for the theta function. Okay, so this is important.
is where you get the functional equation for the L function
The L
in general.
functions.
Right? Same for the zeta function.
Same
right?
for the zeta function.
It's all Poisson summation.
It's all Poisson summation, as Tate taught us.
Great.
Great. Okay, so now what to do is obvious. Actually, it's not entirely obvious yet. It's almost obvious.
You
So-
should do the same computation you did for the zeta.
We're going to do the same computation. Yep. So following Riemann, again, Riemann style, Riemann-Tate style. We're going to look at the Mellin transform of this integral from 0 to infinity. Again, this function has great decay properties at infinity. At 0, you have to be a little bit careful. At 0, you have decay. So if you replace, if you look, so at infinity, this thing is a sum of, this f is in there, which is converging exponentially. At infinity, at t going to infinity, we have rapid decay. Rapid decay. As t goes to 0, well, this thing is whatever, this thing is just going to, this thing's decaying, but I have a 1 over t here. So I have to be a little bit careful. So this is a real part of S is sufficiently large. Real part of S is, bigger than 1 or something.
Then the advantage here is that like in the zeta function, you have to split this into two integrals. In here, you don't have to.
That's true. I actually like to split it into two integrals anyway, to see it from two different viewpoints, because I'll want to express it in terms of an L function. I want to get a functional equation, but there is no region where both the real part of S is bigger than 1 and the real part of S is less than -1 or something, or less than 0. So I want an expression that will capture both of those things. Okay, so this is theta f chi of t to the s dt over t, which when we open up what theta is, theta, recall, is the sum over the positive integers, chi of n, f of nt. So now I have a sum over the positive integers, chi of n, integral from 0 to infinity, f of nt, t to the s, dt over t. And everybody here already knows how to make this change of variables. And so that's just an L chi s, good old Haar measure, f tilde of s.
Now you have to do the other side.
Now we have to do the other side. Now we're going to break it. We're going to break the sum from, now I'm going to be not so careful here, I think. I'm going to integrate from some value big T to infinity, leave this alone. The only question is about what's going on at 0. T to the s dt over t, plus a sum from 0 to t of the same thing. And now I'll use the functional equation.
Interesting, yeah, you're breaking it up, just like in the regular zeta case.
Absolutely. Chi of -1, tau of chi over tq. Now I get this other theta function, theta f hat chi bar of 1 over tq d t to the s dt over t. Let's make that a little clearer. T to the s dt over t. And here I'll make the change of variables. T goes to, so I want qt, or yeah, let's make t, let's replace t by t over 1 over qt. Okay, let's do this as a real change of variables. I'll make u equal to 1 over tq, so that this becomes a just u. Okay, then it'll surprise nobody that du over u is dt over t, made with a minus sign.
But then, like again, you're swapping around.
And to swap the integrals, so let's work on this. This thing is equal to an integral from, okay, u will start, t ended at big T, so this will start at 1 over tq up to infinity, and I switch them because of the minus sign, u over u. There's this finite stuff, chi of -1 tau of chi. There's a theta function. I mean, this doesn't belong in the integral. This can come all the way outside. There's a theta function of f hat chi bar of u. And this is t to the s minus 1. So I'll get a u to the 1 minus s. But the u is equal to qu is equal to 1 over t. So I get a factor of q to the I have to do this a little bit more carefully. So I had a t to the, let's do a little bit more carefully. I had a t to the s minus 1, and t is 1 over qu. So I get a u to the 1 minus s and a q to the 1 minus s also. So what we've got is L chi of s times f tilde of s is equal to an integral from t to infinity f chi t to the s dt over t. I haven't touched this part. Plus a funny integral. Now, if you want to make these the same, if you want to make these over the same range, you can by choosing t to be 1 over root q. Then this will go from 1 over root q, and this will also go from 1 over root q. But you don't actually have to do that if you don't want. Chi of -1 tau of chi, the theta function for f hat chi bar of, should I go back to t as my dummy variable in case I want to combine those later? T to the 1 minus s, and there's a factor of q to the 1 minus s, and a dt over t. Okay, so as before, both of these are avoiding 0. The theta functions have rapid decay, so this is an entire function. This is entire, and we did not need to get rid of the 0 entry, the term n equals 0. So there is no, so that's my proof for you. So now if you take f to be f tilde to be the gamma function, or translate the gamma function if you need to make f odd. So that's the proof that this thing has analytic continuation as an entire function.
You didn't do, there's nothing weird along the way, right? You had an integral from 0 to infinity at the beginning. And you just said, oh, take real part of S to be large enough for whatever is convenient.
Yep.
But then at this point, now you can just look at this as its own expression.
Absolutely.
And then you do.
Yep.
Okay.
Okay, let's since we're already here, let's prove the functional equation. For the functional equation, I'll take t up to infinity. This is true for any t. And this expression holds for any value of s. So I'll take s small enough that I can open this sum and expand things out.
Oh, this feels somehow like a bit more work than the bump treatment.
We could argue about whether or not it's more. I think it's basically identical, but this gives, so it's basically the same thing.
Yeah, I guess the thing with bump is that he does, like, when he sets up the Mellon transform, he wants to say this is analytic immediately, right? And then you have to do all the analysis of checking that right there, whereas here you're sort of doing it as you go.
Exactly.
So yeah, I think probably it's about the same thing. It's just where are you checking it?
Right. So this computation, you see, where did we use the right here? We need the real part of S to be bigger than 1 to even expand this out. Okay, so to be able to reverse orders, we need this to be absolutely convergent, so we need the real part of S to be bigger than 1. For the same reason, we're going to need the real part of S here to be the real part of 1 minus S to be bigger than 1. In other words, the real part of S to be less than 0. And there's no region where both of those agree. So now assume real part of S is less than 0 and send t to infinity. And then we can recover this expression.
And then the tail of the other one dies out, right?
Exactly. So by this, I mean this thing. which is true, which holds for any value of t. So there's no limit to take. It's true for any t. This is equal to, of course, this integral decays to 0 because you're taking it out to infinity. This integral becomes an integral from 0 to infinity, q to the minus s. These are all constants. Chi of -1, tau of chi.
Being entire, you don't have to worry about 0 at all.
Exactly. There's no poles at 1 or at no poles at s equals 1 and 0.
In contrast to zeta.
In contrast to zeta, that's because chi of 0 is 0.
Right.
So there's nothing to take out from the theta function to make it a sum on the integers. And what is this? By the same calculation, well, okay, let's stick it in. This is a sum over positive integers, chi bar of n, f hat of nt, t to the 1 minus s dt over t. So you see, for this to make sense, I need the real part of s. For me to be able to reverse orders right now, I need the real part of 1 minus s to be bigger than 1, which means real part of s to be bigger than 0. So then this becomes a sum. Let's just do it. We're already here. Chi bar of n. Of course, there's this stuff in front.
-1.
Yeah,
tau
q to the
of
1
chi.
minus s, chi of -1, tau of chi. I want this to be a tau of chi over q and q to the minus s. Am I missing something here? Did I lose a factor of 1 over q? I have my 1 over q here. This is du over u. What happened to the 1 over q here? Well,
But that only came from the other factor, right?
yeah.
Maybe it was sort of forgotten.
The t I pulled into here, so this became t to the s minus 1, but the q I dropped.
Right.
1 over, okay. And so this q to the s minus 1 with an extra q is just q to the minus s.
Right.
That's much better.
So
That's a q to the minus s.
So many things floating around.
This is a q to the minus s. Yeah, if you guys can catch me, that's much better than
Sorry.
having to fix it later. No, it's on me to get it right. It's not on you to fix it. Okay, and then we're going to get exactly as always over n to the 1 minus s, and then f hat tilde of 1 minus s. So it's f hat. We made a change of variables. T goes to t over n. That brings out an n to the minus s. This is the range where this converges absolutely. And so you get q to the minus s, chi -1 tau of chi, and then L chi bar of 1 minus s, and one more term, which is, let's put it here, f hat tilde at 1 minus s.
Q to the minus s, that's entire, right?
Yeah.
So,
The point is, this is the functional equation.
right. Oh, yeah.
So we already had the analytic continuation. Now we have a functional equation relating Ls chi to L1 minus s chi bar. So now we have the functional equation.
What's up with that? Q to the negative.
You mean q to the negative s?
Q to the negative.
That needs to be there. There's a balanced version of this where you put q to the I see what you're confused about. You mean in functional equation in terms of s going to 1 minus s.
Yeah,
Okay, so
yeah,
let's do
yeah,
one
yeah.
last thing. Let's put a q to the s over 2. If I multiply both sides by q to the s over 2.
Exactly, that's what's going to balance it out.
Yeah. I'm not sure if it's s over 2 or minus s over 2. We'll see in a second. Okay, so let's do a final version of this. L chi s f tilde of s. So if I multiply this by q to the I want this to be q to the 1 minus s over 2. I'm missing a q somewhere.
Right, that's what
I'm missing a
saying.
q. I want this to be over root q. Oh, I just put it in. Yeah, sure. Okay. I'll just put it in. Chi of -1, tau of chi over root q, and I'll multiply in a root q.
Ah, I see. And this root q is related to the magnitude of the
Yep.
Gauss.
Yep, and let's do that actually, since since we were almost there. L chi bar of 1 minus s f hat tilde of 1 minus s. Okay, now you're happy, right?
No existential phrases.
So there's s's on this side, there's 1 minus s's all on this side.
Right, okay.
So I just multiplied through by q to the s over 2 on both sides. That gave me q to the minus s over 2. And then I borrowed a factor of root q from the top and bottom to make it like this.
Right.
So
Like
now it's,
the completed version, sort of like the C for.
yes, exactly.
Zeta.
Yeah. In the case of, yeah, so when f for f equal to either e to the minus pi t squared or e to the minus pi t squared times t, to make it even or odd, this thing is called the completed L chi of s. And this thing with the q, but not with these factors. So we get an equation like this. This is chi of -1 tau of chi over root q times the L function of pi bar at 1 minus s times the completed L function of pi bar at 1 minus s. And this thing, so the next thing I want to claim, and maybe we'll finish with that, is that this thing has absolute value 1. So this is like a root number.
Yeah, Bump does this ugly thing, right, where he has to add an epsilon to all the exponents in order to separate like the even and odd.
Which is exactly just whether f needs to be even or odd. But there's no reason to treat them separately. It's the same exact thing.
It's true. It's like now I wonder why does it even pop?
Well, but look at what happens. The Fourier transform of this is just the same one that we had for zeta.
Oh.
But the Mellon transform, first of all, the Fourier transform changes.
He gets to treat them separately, and he does do that.
Right. But this function, this equation has nothing to do with whether chi is even or odd. It's just always true.
That's a good point. Yeah.
If you define it like this.
So if you take a specific case, then you might have to go further and simplify the Fourier transform.
Right.
Okay, so if we pick the wrong, the odd one from even higher, both sides just vanish.
Yeah, exactly.
Okay. That says a lot.
Yeah,
It'd be like zeta of 3 or
it's
whatever.
exactly the
You
same
get-
problem as zeta of 3. Yeah, you get a nice identity for zeta of 3, but the numerator is 0.
Right.
So you get no information. Okay, so let's see why this is absolute. So in other words, if chi is primitive, so this is my real claim, i.e. I'm claiming if chi is primitive, then the absolute value of tau is root q.
Yeah,
So
Bump
that's-
actually needs this to even get this far,
To know that it's not 0. Yeah,
because he doesn't do the Fourier analysis stuff at the beginning.
exactly. So why is that true? It's just Parseval. Remember Parseval, which is why I wanted this normalization to begin with, all the way back at the beginning. Oh, too far. Where's Parseval? Oh, here it is, Parseval.
Right.
So let's remember Parseval. It's just going to be an immediate consequence of Parseval. Proof. Okay, Parseval says that if I have the L2 norm of chi squared, that's the same as the L2 norm of its Fourier transform. The L2 norm of chi squared is the sum over R of Q, chi of R norm squared. But of course, this is non-zero only when R is prime. And when R is prime, the absolute value is 1. So this is just phi of Q. Now let's look on this side. This is a sum over M mod Q, chi hat of M norm squared. If chi is primitive, then the only M's that contribute are the ones that are co-prime to Q by our exercise. And for those, this is equal to chi of M bar times
chi
chi hat of 1, chi hat of 1, and chi hat of 1 is tau of chi over root q.
Right.
Over or times. My normalization is that tau is equal to tau over root q, over. That's right. Okay, so this is a sum over m mod q prime, absolute value of chi of m bar squared, absolute value of tau of chi over root q squared. Okay, this is a constant that comes out. This constant tau of chi squared over root q squared comes out, and I have a sum over this of something of absolute value 1, so that's v of q. And these two things are equal. So that's it. So the phis cancel on both sides, and tau has absolute value root q. So it's Parseval. It's just Parseval.
This is a great case for doing Fourier analysis generally.
Generally.
Like using it like for each individual case.
Yeah.
It's kind of nasty to see it for the finite case separately from the
Yep.
infinite case. They need to do everything twice.
All right. So with that, we have succeeded in our first endeavor, which is to show that LS chi is entire. And in fact, we gave a functional equation and so on. The next thing we need is so let me leave you with a little some identities that are kind of cool. So this is a teaser.
Give some sums.
Let's give some sums. So this is something that is called the Leibniz Formula. Anybody know what this sums to? So the alternating sum of turns out it's pi over 4.
In India, there's like that.
Exactly.
Really long time ago already.
So Leibniz, it's called the Leibniz Sum, but actually Madhava knew it in the 1400s. Don't quote me on this. 1400s.
He did some approximations of pi with this, which were really bad, right? This converges really slowly.
This converges very slowly. Actually, Madhava had much better approximations to pi, but he also had this formula.
Right.
And what is this? This is just L chi 2 at 1, because chi 2, chi 4, L chi 4 at 1, because the real character mod 4 gives you 1 on the 1's mod 4 and minus 1 on the 3's mod 4, and zeros on the evens.
The class number formula is going to help us sort this out. Right?
Exactly. So I wanted to write down a couple more identities that you guys might enjoy.
And we're going to see the class number formula in as much detail as it's in the same everything else.
Sure.
Yeah.
Oh yeah. So here's one identity. Here's another identity. You know, I'm putting a dot. Here's one. Here's another identity. 1 over 1 minus 1 over 2 minus 1 over 3 plus 1 over 4, no over 5, plus 1 over 6 minus 1 over 7 minus 1 over 8.
This is model what?
Exactly. Yeah, I sort of give it away. Plus no 1/10, and so on. So this is. Anybody know what this sums to? Louis, do you know what this sums to? It turns out it's twice log of phi over root 5. Phi is the golden mean. 1 plus root 5 over 2.
And the explicit formula is number 3.
This is the real character mod 5 at 1. Okay. I'll just give you the last one. 1 over 1 plus 1 over 2 minus 1 over 3 plus 1 over 4. Yeah, what about the sequence of pluses and minuses? The 1 and 4 are the only squares mod 5, and 2 and 3 are non-squares. 1 is a square, 2 is a square, 3 is not, 4 is a square, 5 is not a square, and 6 is not a square, mod 7. And this formula comes out to pi over root 7. That's the real characters. these are the real characters. So this is L, the real character mod 7 at 1. There are two, this is a 2. Anyway, I think this is right. So let's check these numerically, and we'll see if they're right. But so this is there's an infinite collection of such identities that Dirichlet identified. For any sequence of these plus signs and minus signs, Dirichlet can tell you what the answer is on the other side. And as you can see, sometimes it's pi, sometimes it's log of phi or something. What is going on? Why is this